count. That doesn't add up. You need taking some math too.
I'm already taking that. I also am taking, I think, micro, which is the only one I have to.
Micro.
Okay, so we are talking about particle statics. Does anybody have any homework questions you'd like me to go over that were confusing?
The center of mass in the one tripped me up, but I just kind of realized that it was just arbitrary.
Yes, right. You don't the one, the sort of J-shaped thing.
Yeah.
Yeah. So that was just given to you, so you can just, that's just a name for a point, that's given. We'll talk about calculating centroids pretty soon, but not yet. And so nothing else? Everybody is okay with the homework for now? Okay, so we're doing particle statics, and
I have a question.
yeah.
Are you going to be posting answers at some point for the homework? Just
Uh,
on the off chance?
No, just the solutions that are posted.
Okay.
Yep. But, and I don't have those answers, but I'm always happy to go over problems in class. So, all right, and we're talking about the types of contact forces. So we're in 2D particle statics. And we're talking about contact forces. And there are three of them that we're going to deal with here. The first one is forces applied by cables. The second one is frictionless contact. And the third one is friction contact. And last time we talked about cables, so now we're going on to frictionless contact. So if two objects push on each other without friction, the force is perpendicular to the surface of contact and toward the chosen body. Okay, so remembering these definitions is a good idea. Because if you sort of do it intuitively, there are always cases that come up that sort of confuse your intuition. But if you remember this definition, you can always sort it out. And so, like, for example, if you have, that's supposed to be straight, a little better. So if you have these objects, let's say this has a mass of 7 kilograms and it's pushing on another one with a mass of 5 kilograms. And let's say there's some force up the ramp to cause a contact force between these two bodies. Then the free body diagram of the 5 kilogram So there's the outline. The weight force is straight down. The weight force doesn't care anything about what the motion is like, what the angle of the surface is. It just points straight down. So there's a weight force of 49.05. That's 5 times 9.81. And now there's two places where the surroundings make contact with this body. The ground makes contact with the wheels. And since this is a particle, we're treating everything like a particle now. I'm just going to put it on one single wheel instead of spreading it out over those two rows of wheels. And this is a pushing contact without friction. Wheels are always just sort of a shorthand for saying no friction, unless something about the problem says otherwise, that there's some kind of rolling friction or something. So the rule says perpendicular to the surface, and the surface is the ramp. Okay, and toward the chosen body. We don't know what that magnitude is, so I'll call that N 5, because that normal force will be different than the one that's on the 7. And notice those two vectors are not parallel to each other. That's important. And then the other place where the surroundings make contact with the boundary is where the 7 touches the boundary. That's a pushing force. There's no reason to believe that friction is contributing here. So that force is going to be perpendicular to the surface, toward the chosen body, and I'll call that R.
For
Reaction. So N is for normal, like you always use that in physics. R is for reaction, which, I don't know. You could use, both of these are reaction forces. But N's and R's are pretty common variables to use for pushing forces. And now we're going to go to the free body diagram of the 7 kilogram. There's a weight force down of 7 times 9.81, so that's 68.67. There's a pushing force from the ramp, so perpendicular to the surface, toward the chosen body. I'll call that N7. There's the 100 Newton force that's given. We don't have to know what that's from. And then there is a pushing force applied to the left side by the 5 kilogram cart. So that's perpendicular to the surface, toward the chosen body, but now the other body is the chosen body. And since this is a contact pair, this is a Newton's third law setup. And so this magnitude has to be the same as that magnitude. So this is from Newton's third law. Any questions about that? And then the last type of contact force that we're going to use for particle statics is friction contact. And friction contact, okay, so like in physics, you always talked about friction in terms of a normal force and then a friction force perpendicular to that depended on the normal force. You use the coefficient of friction. We're not going to worry about that here. And the reason we're not is these are all going to be, well, almost all, they're all going to be no acceleration. Most of the time, it's going to be static friction. So you can have no acceleration and not have the thing at rest, right? You can have that because it can be moving with a constant velocity, okay? And in that case, you would have kinetic friction. But most of the time, we're going to be talking about things that aren't moving. So nothing's going to be sliding. So we're in static friction. And when you're in static friction, you can't determine remember, you can't determine the friction force based on the coefficient of friction and the normal force. All you can figure out is an upper bound for it. Remember that? So in order to calculate the friction force, it's just not useful for us to know the coefficient. It doesn't help us at all. And so we're just going to treat this in this class as a force vector with an unknown direction. So for example, if you have a ramp and let's say this is a 2 kilogram block sitting on the ramp, and then there's a 1 kilogram block sitting on top of it. And let's say there's a horizontal force here of 5 newtons. And a force parallel to the surface here of 10 newtons. Those are pretty big forces compared to those masses now that I think about it. Let's make those a little smaller, make it a little more plausible. Okay, so the free body diagram of the 1 kilogram cart, 1 kilogram block. You have a weight force down of 1 times 9.81. You have this horizontal force that's just given. And the last force we have comes from the contact at the surface applied by the 2 kilogram block. We're assuming that this and this are both friction contacts, okay? So I'm going to represent this the way I represent forces with unknown directions. I'm going to draw like a little coordinate system. And I'm going to use the notation, the force on the 1 kilogram by the 2 kilogram. And that's a vector. And this F12, well, let me write it more generally. So let's say the force vector FAB is defined as the force on body A by body B. And that notation is going to be really useful to us. The main reason that this is a really nice notation is that what it then says about Newton's third law, okay, is that the force on body A by body B is equal and opposite to the force on body B by body A. Okay. So we're going to use this notation a lot, and this is the real benefit of it. Anybody have any questions about, like, is it sort of clear why using this notation, that is just a simple, like nice clear statement of Newton's third law. One thing that's kind of annoying about this notation is that not everybody uses the same order of subscripts. It tends to be more common that for physics people, they're used to this meaning the force body A applies to body B, like the reverse meaning. But in this class, I'm going to always be super consistent about this. And in engineering classes, this is the more common way of doing it. So the first one is the body that the force is applied to. Or the first one always is your chosen body, what you're drawing the free body diagram of. And the second one is the thing applying the force. Okay, so now we'll go to the free body diagram of the 2 kilogram. We have a weight force down of 19.62. We have a force this way of 10 newtons. And then the only thing we have left is the force, the friction force applied to the 2 by the 1. So this is, I'll write it as, this is the force on 2 by 1. Okay, well, this force, if the subscripts are different, the variables are different, right? Subscripts are just kind of a way to say these things are kind of in the same category somehow, but they're different variables. So if you're going to try to use Newton's laws to solve equations for all your variables, you want as few variables as possible. So now I'm going to use Newton's third law to rewrite this as negative F12. What am I doing? I need to stop talking and think first. This is the one.
Read my mind.
Yeah, that made no sense. Okay, F21. Pretend I didn't say that. Negative F12. And then this one is also a friction contact that I'm just going to call R or something, you know. Okay, that makes sense now. Any questions about that?
Not anymore.
Yeah. But going back to the thing, you follow what I'm saying about reducing the number of variables. So this is a thing we're going to use all the time when we have multiple bodies and we're trying to solve a problem with multiple bodies. You're going to reduce the number of variables by using Newton's third law on these subscripts. Okay, so this was just the free body diagrams. Now I'm going to do a problem where we'll do the free body diagrams and then we'll actually do the calculation. So let's say we have a ramp that makes an angle of 20 degrees with the horizontal. And there's a pulley here. And we have a 5 kilogram box that's connected by a cable that passes through the pulley to a 1 kilogram. And we're assuming that this is in static equilibrium. And we want to calculate the forces on each body. Okay, we're going to start out with free body diagrams. We're heading towards Newton's law, Newton's second law, assuming that there's no acceleration. Okay, that's what we're always going to use for particle statics in static equilibrium. And so if you're using Newton's second law, you always have to draw free body diagrams. Okay, so we have a weight force down of 49.05. For this to be in static equilibrium, this has to be a friction contact. If there wasn't friction there, this thing would accelerate. So there are two places where the surroundings contact the boundary. One is the cable. So the force on this body is parallel to the cable, away from the body. And the second one is the contact with the ramp. And so I'm going to write that as R. You could write that as force on body 5 by the ramp or something, F5R. But it's really only helpful to use that notation if you're going to then turn around and draw a free body diagram of the other body. We're not going to isolate the ramp. That would bring in more complications than it helps. And so it doesn't matter what you call that. Are you with me on that free body diagram? Okay. And then, well, I guess let's go to Newton's second law for this. And then after we're done with this, what we're going to see is we can't solve this by itself. And then we'll isolate the second one. Okay, I'm using a standard coordinate system, so the weight force is 0, negative 49.05. Then the reaction force from the ground is Rx, Ry. Then this cable force, here's the coordinate system. There's the force. It has a magnitude of T. And this angle is 20 degrees. So this is going to be T times cosine and sine of 20 degrees. So that is 0.940 T, 0.342 T. That's all the forces in the free body diagram, so we're done. And that's equal to the mass times the acceleration, which is 0, so we can just set all this equal to 0. Can we solve this? No. How do you know that? Because I said that we weren't going to be able to solve it. But you also know that we have 2 equations and 3 variables, so that's never going to work. So now we're going to draw the free body diagram of the hanging mass. The weight down is 1 times 9.81. The only contact with the surface is from the cable. So that's parallel to the cable, away from the body. It's the same cable as in the other one, so this is T. We're assuming that there's no friction or mass on the pulley and no mass on the cable. And so Newton's second law for this says 0 positive T plus 0 negative 9.81 is equal to 0, 0. You can treat these all of these component equations, you can just treat them as single equations. So you can think of this as equation 1, equation 2, equation 3 is useless. That just says 0 equals 0, which you already knew from your previous math classes. And then equation 4. Well, I don't know. Maybe I'll just make this equation 3. But now we have 3 equations for 3 variables. So we can say, okay, so equation 3 tells us that t is equal to 9.81. Now we can plug that into equation 1. So we got Rx plus 0.940 times 9.81 is equal to 0. So Rx guess I gotta calculate that. Rx is equal to negative 9.22. And then plug it into equation 2. And you get that negative 49.05 plus Ry plus 0.342 times 9.81 is equal to 0. So Ry is equal to positive 45.70. And now you could go back and, put those back into the free body diagrams and show all the external loads on both of those two bodies. Well, this was a system of 3 variables for 3 equations. It's a little tedious, but doesn't take forever to do that by substitution. But we're going to have problems where I know at least you're going to have problems eventually with 15 equations and 15 variables. And you really, really would rather not do that by substitution. Okay, so I don't know how many of you need to know this, but there is a way on your calculator to solve systems of equations with any number of variables sort of instantly. So I want to just make sure everybody is comfortable doing this. So this is for solving big systems of equations, linear equations. And linear equations is all we're ever going to have in this class. And it's called reduced row echelon form. And it's abbreviated RREF. So step 1, write out all your equations. With all your variables on the left. On the left side of the equation. And your constants on the right side of the equation. Then write what's called the augmented matrix for this system of equations. So let's say that this is an n equation system. And the way you do this is just arbitrarily choose an order for the variables. And you're going to write out a matrix that has, okay, so these are the equations. The rows going across represent the different equations. So there'll be n of those. The columns represent the variables in the order that you chose. And there'll be n of those variables, and then there'll be an n plus 1 column that is the constants. Okay, so this, there are going to be n rows, and there's going to be n plus 1 columns. The values in here are the coefficients of these different variables. And so I'll show you what that looks like. But if you're, so for example, for equation 2 here, your coefficient for your variable ry would be 1. Your coefficient for your variable t would be 0.342. Since you have to get your constants on the other side, your constant would be filled out with positive 49.05. I'll do examples. But now the third step is run the program RREF, and every TI calculator has a version of RREF. And you'll do that on this augmented matrix. And the output is going to look like this if it works. The only way it doesn't work is if you've entered something wrong, or if the problem isn't solvable through statics, which can happen. You know, you have redundant forces or whatever. But most of the time, you know, we'll be working on problems that are solvable. And so the only way this will go wrong is if you fill out the matrix wrong. But the output is going to look like this. You'll have n rows, n plus 1 columns. and the first n by n matrix on the left is going to look like an identity matrix with just ones on the main diagonal and zeros everywhere else. And the only reason that's useful is to tell you whether this worked or not. If you don't get this identity matrix here, something crashed with the program. And the last column are your solutions to the variables in the order that you chose. So this is going to be the variable 1 solution, variable 2 solution, and this is the variable n solution. Okay, so let me just show you how this works. I guess let's do it first. Well, let's do another example and use it in another statics example. Any questions before I go on? All right. So let's say we have a ramp that makes a 30-degree angle with the horizontal. A 50-kilogram cart here and a 20-kilogram cart here. And there's a force pushing the 20 into the ramp of 100 newtons. And then there's a force F here, and this is in static equilibrium. So free body diagram of the 50. We have a weight force down of 490.5 newtons. We have a pushing force from the ramp. I'll call that N50. That's a frictionless contact because the wheels are drawn in there. We have a pushing force from the 20 kilogram that's perpendicular to the surface toward the body. So I'll call that R. And then we have this force F. Newton's second law. I'm going to use just a standard coordinate system. And I'm going to always do that on like whether there's friction or not. I'm not going to rotate the coordinate system along with the ramp the way that you did in Physics 1. Okay, so representing that force vector, that makes, so to go from the positive x-axis to that vector is a positive 30-degree angle. So this force vector is F times cosine and sine of 30. Okay, so that's 0.866 F, that's the cosine of 30. 0.5 F, that's the sine of 30. Then you have the weight force, 0, negative 490.5. This N50, okay, so here's our coordinate system. We know that this normal force is perpendicular to the surface, so I'm going to draw a vector parallel to the surface, and then I'm going to draw the vector we want perpendicular to that. This angle is 30 degrees. This angle is 90 degrees. So for that normal force vector, you go plus 30 plus another 90. So it's cosine and sine of 120. So that n50 times cosine and sine of 120 is negative 0.5 n50, and then positive 0.866 n50. And then the last one is this r. That is perpendicular to the vector, that f vector, okay? Not perpendicular, exactly opposite, I mean. So it's, so you can think of it as this plus 180. So it's going to be 210 if you want to use the angle. Or you can just think of it as the opposite of this. And it's going to be negative 0.866 f, negative 0.5 f. And that's equal to zeros. Anybody have any questions about that one?
Yeah, you're just saying it's opposite because it's not moving.
No, I'm not saying that actually. I'm just looking at the direction of the vector.
Yeah, you meant.
Oh, gotcha.
Yeah, so I'm just saying, oh, this should be, yeah, sorry about mistakes like that are confusing. Should be R, right. So I'm just looking at the directions of those vectors and figuring out what my cosine and sine angle are based on, you know, how they relate to other vectors on here. Okay, so we got our first equation, equation 1. Here's equation 2. And now we can go on to free body diagram of the second cart. So this is the 20. The weight force is straight down, and that's 20 times 9.81, so 196.2. There's 100 Newton force like that. A normal force from the ground, I'll call N20. And then there is the pushing force applied by the 50 kilogram cart, and that has to have the same name as the other one. And now Newton's second law, we have 0.866 R, 0.5 R. That's cosine and sine of 30 degrees. This 100 Newton force is the opposite direction of this normal force we already figured out. So you can just switch the signs on both of these components. And, you know, so it's going to be, that unit vector is going to be positive 0.5, negative 0.866. And then we'll multiply it by 100. So that's going to be 50, negative 86.6. And then the N20 is going to be negative 0.5 N20, positive 0.866 N20. And then we just have the weight, 0, negative 196.2 is equal to zeros. Okay, so how many variables do we have? We have 1, 2, 3, and then a fourth one that's n20. So we have 4 variables and 4 equations. So we should be able to solve this. The variables were R, N50, F, and N20. Okay, so now I'm going to make the augmented matrix. It needs to have n rows and n plus 1 columns. So it's going to have 4 rows and 5 columns. The rows represent equations 1, 2, 3, and 4. The variables can go in whatever order you choose. So I'm going to choose R, N50, F, N20. And then these are the constants. And so equation 1, R's, we have negative 0.866. N50s, we have negative 0.5. F's, we have 0.866. N20s, in equation 1, we have 0. And constants, we have nothing. Okay, now equation 2, R, we have negative 0.5. N50, we have 0.866. F's, we have 0.5. N20s, we have 0. And constants, remember the constant has to be on the other side of the equation, so that's going to be positive 490.5. Equation 3, R's, we have 0.866. Constants, we have negative 50, because you have to get it to the other side. And N20s, we have negative 0.5. Everything else is 0. And now for equation 4, R's, we have 0.5. N50s, 0. F's, 0. N20s, 0.866. And the constant is positive 196.2. Yep.
Negative 86.6 doesn't need to be moved over?
It does. I didn't see it there. So you have to add those together. Thank you. So that should be positive 282.8. Okay. Well, we're out of time, but let me just quick punch this in. And so your different TI calculators have different ways of doing this. On the 84s, 83s, 86s, you have to go to the matrix environment to edit the matrix, put this stuff in, and then you call RREF. For the 89s, you can just enter the matrix. Actually, for 84s, I think too, you can just enter the matrix on the screen. The TI-89s also have a thing called linear equation solver, I believe. That it's a sort of an easier environment for doing this. And then, yeah, the Inspire, you punch in the matrix by going to the matrix button. All of that stuff you can find. You can find details on how to do that in the appendix of the statics textbook that's on D2L. So look for RREF on that if you want more details. But okay, I'm going to do this as, so number of rows, we have 4, number of columns, we have 5. And I don't mean to rush this because I want to rush reduced row echelon form. Next class, I'm happy to talk about it as much as you want if you're having trouble getting this stuff to work. I'm just rushing because we're out of time. But the answers you get are R is equal to 421.76. N50 is equal to 424.79. F is equal to 667.02. And N20 is equal to 83.05. Okay, we can talk about that more next time. That's all.